I would like to welcome our next speakers, Denise and Mike from DM, and they'll tell us about their journey into semantic search. Oh gosh, in an omnichannel retail environment. Please welcome our speakers.
Yes, thanks. Welcome to our journey to semantic search in omnichannel retail at dm-drogerie markt. My name is Denise Schäfer and I work as a full-stack software engineer at dm-drogerie markt for our online shop and our mobile app. 5 years ago, we founded a dedicated search team, and since then, I try to improve everything related to search.
Hi, my name is Mike Dirnberger. I'm working as a backend software engineer at DYE Conclusion, and I'm helping clients to design, implement, and optimize search solutions from open source to commercial solutions. And of course, my favorite client is DM, where I'm part of the search team for the last 5 years. Okay, what we'll cover today. First, we have a few examples to highlight the value of semantic search, especially for our domain as we see it. Then we take a look at the technical stack of our semantic search solution with vector search and how we measure and evaluate the quality of our search results. Then we take a look at the steps and our process of optimizing semantic search, the steps we were going through. And the last step, we show the concrete use cases that we use semantic search for at the moment at DM, and maybe future use cases as well.
Yes, dm-drogerie markt is Germany's #1 drugstore chain and is becoming very important in the European market as well. The key facts are that we have over 4,000 stores across 14 European countries, and we handle over 2 million searches every day. That happens across our 2 digital touchpoints, like our website and our mobile app. Our search challenge includes a huge product catalog, and yes, customer searches very different vocabulary. And if our search returns 0 results, it hurts, of course. And our search must not only work in our website, but also in a chatbot and in AI assistant integrations. Yes, the first slide shows the gap between keyword and semantic search. Keyword search relies on exact word matching and, yes, don't understand intent or meaning. This is where semantic search comes in. And we can see this in 4 common failure cases. The first is synonyms. Ohne Zucker, misses products labeled as sugar-free. Semantic search can connect those. And the second is words that change meaning by context. In lip liner Beere, Beere is not a fruit, it's a color, and semantic search can get this. The third is hidden intent. Someone searching for blaue Flecken wants a remedy like arnica cream, and keyword search can't figure that out. The last is unclear or tricky questions like learning how to drink. Those queries are hard to interpret, but semantic search can suggest something related. Yes, now let's have a look at our technical foundation. If a user types a query, our E5 encoder encodes the query to a vector, which captures the meaning of the query. Our E5 model is very fast, compact, and works across several languages. We run it via Onyx runtime, so it fits neatly in our existing Spring Boot and Kotlin services. The next step is that we use Quadrant as our vector search, and it performs approximate neighbor search in the vector space to find the most similar products. In addition, it applies attribute filtering as native filters. On top of this, our business logic applies filters and boost and re-ranks our results. Overall, our semantic search runs at P95 latency below 50 milliseconds end-to-end. Yes, here you can see how we measure quality for our search. We have different approaches. First, we use offline metrics. Here we measure NDCG at top 10 and top 30, and therefore we derive relevance scores from our clickstream data, like clicks, add to carts, and orders. We also apply a position bias correction. And those offline metrics run whenever ranking and embedding changes in our pre-production environments. The second approach is LLM assistance relevance tests. We use it if we have two less business metrics for a query. And we run it also in pre-production, and also we use production queries as test input. Here an LLM judges our query result pairs and provides relevance ratings with explanations. And third, we have A/B testing in production. Here we run controlled traffic splits on live queries. We measure key business metrics like click-through rate, add to cart conversion, zero result rate, and we use A/B testing also to analyze long-term relevance trends.
Okay, now that our setup is in place, it's time to focus on optimization. Here we outline 5 iterations that we've gone through in the process. At this first, we set a few guardrails, like a global score cutoff and a category restriction. Then we integrated business signals to get a more similar ranking in our semantic search than with the traditional keyword search that is alongside in another system. Then we detected or identified brands, categories, and popular filters in queries to boost brands and to increase relevance for those queries and also improve precision, actually. Then we tried re-ranking with cross-encoders to get rid of some more irrelevant results with a special score filter. And finally, we used fine-tuning to adapt our embedding model to our domain, which was very important. But the last step, you may ask, why this order? The first stages are easier to implement, and the last stages require more effort. That's why we followed this order first. At this point, a big thank you to everyone who has shared their knowledge in the past few years. So we benefited greatly from the past presentations here. So now the iterations, bit more details for the 5 iterations. How can we set guardrails? Of course, there's a similarity score. We can set a global cutoff to the similarity score, which is, of course, highly dependent of the model. For example, the E5 model only has scores between 0.7 and 1.0. So that's one possibility. We also detected drops of similarity scores within the result. So we said, okay, when there's a large drop, let's find the largest drop that's higher than a certain threshold. Then after the large drop, there may be irrelevant result, and we verified this, and then we cut off after this large drop in similarity scores. So that's one other easy method to cut off. Another one was the category restriction. In our product catalogs, product catalog hits should belong to maximum 1 or 2 top-level product categories. We found this from interaction data, actually. So we can actually restrict results to 1 or 2 categories. I've got an example in the next slide. It's Roggenschrot, actually it's coarse rye, sorry. as you can see on the left screenshot, also children's clothing was returned at first try. Of course, this can happen with a model that's not fine-tuned with a pre-trained model. That always happens. That's not fine-tuned to your domain. And but with the easy category restriction, we could restrict that to only food results, actually, as you can see in the second screenshot.
Yes, the next iteration was to integrate business signals, and the idea was quite simple. We want to show relevant products, of course, but we want to rank the top sellers at the top of each relevance group. To achieve this, we introduce score grouping. Semantic search finds relevant products and then groups them by similarity. Inside each group, products with higher sales count rank first. And in addition, purchasable products always surface before non-purchasable ones. And here you can see that we validated the integration of business signals with offline tests, and we compared relevance-only ranking with relevance ranking with business signals. And as metrics, we used clicks and add to carts at top 10 and top 30, which is a total across all top 10,000 test queries that happens into 1 month of traffic. And the second metric is the NDCG at top 10 and top 30, and this is an average across all queries and a very common quality ranking metric. Yes, and what you can see here is that all metrics go up. Adding business signals improved them, and both engagement and ranking quality improved together. In the next iteration, we extend our semantic search pipeline by applying pre- and post-processing layer. And the first was the quadrant native filtering. Yes, and therefore we extract product attributes before embedding and applied those attributes as native filter during search. For example, on sulfate-free shampoo, we extract sulfate-free and search for shampoo, and we applied sulfate-free as a filter. The second layer was brand boosting. If a user searches for a brand like Baby Love, all products from that brand were boosted in the results. And the third layer is the category filtering. Here we try to detect the category directly from the query. Like in vegan shower gel, there is shower gel detected as a category and the result is filtered to that category. And if no category could be detected, we fall back to the root category restriction based on top result. That was what Mike explained before. Here we can see some examples and how they improved our search. First, again, attribute filtering with a query shampoo without sulfate. Before, you can see that there were mixed results and not all of them were sulfate-free. And after, we have fewer results, but all of them are really sulfate-free. The second, brand boosting for the query Schauma dry hair shampoo, where Schauma is a brand. And before, you can see we have not only Schauma shampoos in the top results, but also other products, and after applying brand boosting, there are only Schauma products left. And the third, category filtering with the query baby shampoo. Before we have mixed results, and and there are some adult products too, and after applying category filtering, the results are focused on baby products. Baby is a category here. Yes, and again, this features was validated with offline tests. We use the same top 10,000 search queries. We use the same metrics, clicks and add to carts and NDCG. And as you can see here, all metrics go up, more clicks, more add to carts and better ranking. But what is interesting here is that we, in addition, used our LLM-based offline testing to see if this feature also improved our long-tail queries. And here we took our chatbot live queries and validated them. An LLM judges each query result pair. And yes, we use a graded precision here as a metric. And the delta you can see below the queries, this delta show how much search was improved for a specific query.
Okay, on to the next iteration. we addressed the fact that there are still too many irrelevant results sometimes. And if you remember the presentation before from Otto, I talk of really irrelevant results that have no interactions. So that's why we classify them as irrelevant, because our bioencoder, the E5 embedding model, always finds something we saw before and lacks precision in this step. Because there's no query document interaction at this step. So a cross encoder can help because you can jointly encode query document into it, and it can filter out the irrelevant queries there. So the cross encoder outputs a new score. And for example, with some popular models that you see below, you can just filter out the negative scores because the cross encoder says that's the irrelevant results. That's the idea. But we looked at some model candidates. Our constraints were non-commercial, must run in the Onyx engine, and must be very fast. So we tried a few candidates that you can see here. Actually, the first one that was pre-trained, that was not pre-trained with German, did quite well also. But of course, cross-encoding comes with a latency cost. So you have to think about, it does not scale for all results. You can only re-rank maybe 100 products if you want to have a fast search experience. So that's why we restricted the tokens that the cross encoder saw to 64 or 128 tokens. Then it got faster, and we also tried the fields that we wanted to encode for the cross encoder. And we first tried brand, title, and category stuff, but we saw that was not enough. Sometimes it performed better when we gave more context. But we also saw it actually should be fine-tuned to your own domain. That's very important also for a cross-encoder to perform well.
Yes, the last iteration was the fine-tuning of our E5 model, and therefore we took our clickstream data and converted them in query product pairs. And we labeled them we labeled them with relevance grades, where grade 3 is a perfect match, and grade 0 means a product might be not relevant for the customer. Yes, we trained with MNR loss. The model learns to rank the right product higher than all other products in the same batch. And the result should be a model that understands our DM products, our DM brands, and our customer language, and all with no extra latency at inference time because encoding happens anyway. Yes, the results was quite interesting here. We trained 4 models and all saw the same positive examples, and the negative ones diverge. We trained the first model with the full data, with all positive and all negative examples, and thought it might be too noisy and hurts quality. But in fact, this model was very successful in our offline tests. But we thought it might be even better if we remove the negative examples from the training data, and thought it might be the perfect quality, but the opposite happened. It wasn't successful in our offline tests. So we re-added the negative examples to the training data step by step, but we couldn't reach the quality of the first model. Yes. So the question was, how do the negative examples help the model? Our best guesses were that MNR is robust to noise and low quality pairs create diversity in batch negatives. And the third experience was that we think that weak signals also contain information that could be used. For our use case, we decided that we will use or try the first full trained model, and that we don't over-optimize training at training time. And what is also important, that we want to apply an adaptive cutoff to fix the result count, what you can see in the top right, that this number is lower than in the other trained models. Yes, now we have seen that we have some iterations to improve our semantic search, but the interesting question might be where we use our semantic search at dm-drogerie markt, because we have also well-performing keyword search. So when we started, we analyzed where keyword search was failing, which was on low performer queries and zero result queries. And actually, our semantic search performs pretty well on low performer queries. Our interaction rate was nearly 20% higher on those low performance queries, and we proved that in A/B testing in production environment. Yes, but it was quite an effort to route every query to the right system. That's why we haven't brought this approach to production in the first place. But the second one, the zero result queries, was easy to implement. Semantic search activates as a fallback when keyword search returns zero results. So this one was our first production use case. And the second one was the integration of our semantic search in our chatbot and in our external AI systems. We have an external MCP server. We will see it later. Yes, it's quite understandable here, because here the semantic understanding is more important. And what is planned, that we combine keyword and vector search for a hybrid search.
Yeah, the first use case is quite obvious. We only activate the semantic search results if the keyword search returns zero results. But it was also important for us to actually show a zero result page, still show a zero result page if the semantic search can find relevant results. That's why we optimized where we try to optimize and remove as many as irrelevant results as possible here.
Yeah, here you can see how user input is handled by our chatbot. The first step is an intent classification. An LLM decides if it's a product search, a general advice, or an FAQ. If it's a product search, attribute extraction is applied and semantic search runs, and results are returned to the user with a natural language explanation. What is interesting here is that we expose our semantic search via model context protocol, so it can be used in other external AI systems as well. Yes, and there's no need to change something on server side. And if you want to try it, we have our MCP server URL here. It's public available.
So what did we see? We see advantages for our traditional keyword search that we still have. We build a new system with semantic search alongside, but we see use cases where we want to integrate both, but we don't want to go full hybrid at this stage, because we rather want to do this on a query by query basis. We already have a classifier for query routing, and we already identified the queries that could benefit from semantic search. So that's our approach to integrate both of them. So yeah, that's our current plan. Thanks very much, and we're looking forward to questions.
Thank you very much, Denise and Mike. Do we have questions or speakers?
Hello, thanks for the talk. In your iteration 3, when it was about named entity recognition, you were filtering for attributes and filtering for categories, but boosting manufacturers. First, yeah, it was like that. First, why? And how did you come up with that? Why explicitly only manufacturer boosting and not the others, or different combinations, or something?
Actually, we did it. It was it seems very short here, but it was a long iteration. I tried several combinations, and this one was the best in our offline test, actually. But I tried, with our data, with our queries, with our customer data, it was the one that works best in offline tests.
And brands and categories are the most popular filters for us.
Great talk, thank you. At the end, you said you built some kind of query classifier to decide for which queries you will use semantically retrieved products. Can you explain a bit how you classify these queries? How do you identify it? What's the criteria?
Actually, we are working on it, but we have this classifier in production in our website to classify pharmacy and DM, classical drugstore assortment data. And we trained it with, synthetic data first, but currently we use our clickstream data that are feed into our classifier every day. And yes, this is the way we train our classifier on a daily way, and we hope that it might work for those low performer queries which were very successful in our first A/B test. So, but it's not implemented yet, but we would follow this approach.
Hi, great stuff. I'm curious about one of the last parts you presented. So if I understood correctly, now on the search results you have either semantic or keywords, right? But not at the same time?
At the moment, yes.
Mm-hmm. Do you see that with combining those to go to a hybrid solution, do you see that you need to get rid of the encoding solution, or is that something that will be kept and reused?
No. We have facets and sorting in place yet as well. So maybe we could try another retrieval solution that can handle both, but we don't know yet.
Thank you.
There's a question at the back.
Thank you so much. That's a lovely talk, and as an avid user of DM, I think this is a great initiative. Except I'm just wondering that you did not mention any changes or stuff that was being done for international speakers as well. I still see that if I would search with English, the searches are going to return like 0 results. Also a very small but maybe important thing, a low-hanging fruit, maybe a suggestion, is like also the composite words. If they are written separately, it also breaks. Wondering, what are your thoughts?
Actually, we used a multilingual model of E5, and that brought a benefit for some queries in the long tail. Maybe we discovered that some Chinese queries or Arabic queries, Cyrillic queries now could be answered. But it's only long tail. So, but that worked already. But we still have to roll out the semantic search in all 13 countries.
Yes, actually it's a work in progress because our chatbot is rolled out in several countries. So yes, it will be available soon, I would say. Yes, a chatbot has a semantic search. The normal search is available in all languages already. The normal, our keyword search is available for all languages and countries we have our store in.
No, it doesn't.
du es verstanden? Hast du verstanden?
Yeah, thanks for the great talk. So just would like to ask something on the offline evaluation. So we saw some NDCG values there, but the thing was you apply vector search only on the zero result searches. So actually, probably you don't have historical clickstream data on the items. So how you calculate NDCG was based on your own label. So you labeled some of the query item pairs. How did it work? Just would like to ask this question.
Very good question. For this use case, we first used the LLM as a judge approach with different metrics. And in the A/B test, we just looked at the interactions that happened in the B group, and of course at the revenue metrics and conversion metrics and stuff like that. And we saw actually in the A/B test, we saw additional interactions, additional conversions, and a revenue uplift. But we also saw in the B group that there are still results with no interactions. So still some work to do.
Okay. Let's thank our speakers again. And we're now